Good morning, gentlemen from United States, and Professor Kramer. He is co-chairing the session with me. Professor Kramer, if you would like to introduce briefly.
Yeah, also good morning all over the world.
Mm-hmm. So we start this session with Professor Costa, and the title of his presentation is Using Impedance Spectroscopy to Characterize Materials. He's from University in Aveiro, and as he informed me, he is currently in Calais on a visiting appointment. With that, I give the floor to Professor Costa for his presentation. Professor Costa.
Thank you, Professor. Nice to see you again. I would like to start to thanks to the organizing committee for inviting me for this presentation. I will talk about impedance spectroscopy, and I will try to show you as simple as possible how can have information in materials with this technique. So I am from the University of Aveiro in Portugal. Okay, then I will start the contents of this presentation. I will start with basic concepts. Then we talk about relaxation models, and finally we will we'll see some applications. So, what we do exactly in my team, we use impedance spectroscopy. Let's say you measure exactly impedance. We have here the impedance with the real part and the imaginary part. So this Z is a complex entity. The impedance in what you do exactly is to measure this impedance with these two parts, this real part and the imaginary part. In many cases, we can calculate, of course, the inverse of this impedance that we call the admittance. Of course, it is also a complex number with the real part and the imaginary part. These are, of course, macro properties, as these properties depends of the size and of the shape of the material or the samples that I have. But usually we prefer to see this in, let's say, micro properties, trying to calculate the permittivity. That is, of course, also a complex number with the real part and the imaginary part. And also, in some cases, we prefer to calculate the inverse of this permittivity that we call the modulus. Also, of course, with the real part and the imaginary part. Let's say with this simple measure of impedance, we can actually to have let's say four entities that you can calculate. So depending on the material, depending on the results, depending on the data, sometimes you can use one or other. So impedance spectroscopy, of course, it is a technique that uses frequency domain. But let's say what happens in time domain. So what we can do, we can apply the electric field here. Okay, it's here, and with this applied electric field, we can align the dipoles that are inside this sample. Okay, in this situation, you can see that all the dipoles are aligned with the electric field, and then at a certain moment we cut off the electric field, and we can, let's say, to calculate the depolarization, that is this curve here. Okay, that means it is more or less related with the number of the dipoles that are aligned with the electric field. Of course, after a certain time, the dipoles became in the first the initial positions before the application of the electric field. They means they are there's no more electric field applied, and these dipoles are randomly collocated. So when we apply the electric field, we can orientate the dipoles. Then we cut off the electric field, and we see the depolarization of these dipoles. And you can measure exactly this. And this sometimes, okay, in simple cases, this is exactly an exponential function. So, so this exponential function, you can write it like this. So the polarization is initial polarization. You have an exponential, decreasing the exponential, so minus t over tau. This is called the relaxation time. So we are here exactly in time domain. Okay, so in time domain we see the depolarization, and in some cases this is exactly an exponential. So we can use Fourier transform and to pass to frequency domain, and then you can have the permittivity. And in this case, you have here the permittivity as I see a complex number, okay, and this permittivity is function of the frequency, okay, and we have here the permittivity at very high frequencies and the static permittivity, very low frequencies. And here we have the relaxation time. Okay, this is exactly the case that we see in the frequency domain that corresponds to this case in time domain. That is, if the depolarization is exactly an exponential, we can have in time domain exactly this function that describes the behavior of the permittivity. So, how can we present the data? We know that epsilon prime usually in many materials decreases with frequency. That is when we increase the variation of the electric field at a certain moment, the dipoles cannot align it with the electric field that is moving very, 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 very quickly. And then usually epsilon prime decreases. We have something like that. So here we have exactly this epsilon static, that is the permittivity at the very low frequencies. And here we have, at yellow, we have, let's say, the epsilon infinite, that is the dielectric constant at the very, very high frequencies. And with this curve, we can also have the epsilon double prime, that is the imaginary part of the complex permittivity. We have a peak here, and we can move from one to other using Kramers-Kronig relations. But what we can see here exactly at this point, this red triangle, that is very low frequencies, epsilon prime is very high. Then when we move to this new representation that we call plot, you have exactly here epsilon static, that is the red triangle that corresponds to this red triangle here when we make this initial representation. And here the yellow triangle, it is, let's say, a low value of epsilon prime that corresponds to very high frequencies. So we add this side. And in the middle, more or less, we know that epsilon prime here, epsilon double prime as a maximum. So we see the epsilon prime decreases here. So the frequency increases from the right to the left. So it passes from here to here. And epsilon double prime passes to this point that it is the maximum that corresponds to this point here, this green triangle, it's here. And this corresponds exactly to this maximum frequency here, okay? So this representation, okay, I will show that it's very useful for us to understand materials, and let's say what kind of information we can have from it. So starting again with this simple model, that is the model that corresponds to this pure exponential depolarization in the time domain, that as we saw correspond to this representation in the frequency domain. Okay, and we can do simple calculus to have the real part epsilon prime and the imaginary part epsilon double prime, and you have simply to multiply this by the conjugate, and you easily you obtain this expression for the real part of the complex permittivity, and this expression to the imaginary part of the permittivity. Then we can manipulate these two equations, very simple, and we obtain this new equation that is exactly an equation of a circle. So we see this epsilon double prime minus this quantity, okay, plus epsilon double prime minus 0. This is equal to the radius square. So this is exactly the equation of a circle. That means if I make a graphic of epsilon double prime as a function of epsilon as a function of epsilon prime, I must have exactly a circle, and this is the case. We have exactly here this circle. So this corresponds only for this model, that is the Debye model. That is the model that corresponds to, in time domain, to a depolarization that is exactly a pure exponential. And then we can say that, okay, if you have this Debye model, we have exactly in this cold plot, we have exactly a circle. And the circle, as you see, the center of the circle, it's here, okay? Epsilon static plus epsilon infinite over 2, okay? And 0, 0, because here you have epsilon double prime minus 0. So the center is exactly here. This means that the center of this circle is exactly in this x. So if you have a representation epsilon double prime as a function of epsilon prime that show me a perfect circle, and the center of the circle is exactly here in the x, we can say that we can use the Debye model. That we can see that it's actually a pure exponential depolarization function. So, but in many cases, of course, we have not this Debye model. This Debye, as you see again, this equation, this is the simplest, but in many cases we have not exactly this very nice circle. So we change a little bit this equation, okay, and you use different models. For example, col that you put here an exponent, okay, and this alpha 1 minus alpha. Of course, if alpha is 0, this col is exactly the Debye model. We can also use this Cole-Davidson, more or less it's close to this one, but this exponent is here, okay, 1 minus alpha. Again, in this case, we have if alpha is 0, so we are again in Debye model, okay. In any other case, you can use also two exponents here, okay, that, let's say, this mix the Cole with Cole-Davidson functions that we call Avrili-Aknagami. So there are other functions, but usually it's enough to decide what kind of model we can have, and let's say how to choose exactly this model. So how to choose the model? So first thing, we can do epsilon prime as a function of epsilon double prime. We can also do not only the permittivity, but all the four entities that we talk in the beginning of this presentation. So we can do in not only in the permittivity, we can do it in the impedance, we can do in the admittance, we can do in the modulus, and also we have more or less the same behavior. So if we correctly put epsilon prime as a function epsilon double prime as a function epsilon prime, if I have exactly this circle, I have the center here, so this angle here, it is 90, okay, and we are exactly in the Debye model, so we are exactly in this equation. Let's say what happens when we put here this exponent alpha. So what happens exactly in this cold model? This transforms this circle. This is again a circle, but the center is here. It's below, clearly below the x. So if you have a circle, let's say this angle, this side, it's equal to this angle, this side. Let's say that you have a circle actually, but the center it's here. So we are in the cold model, and we know that exactly this angle here, it is alpha multiplied by 90 degrees. So again, we see if alpha is 0, okay, this angle is 0, so the center is again here. So again, we can see that cold transforms to the debye model. A third possibility is if you have not exactly this circle, but a deformed circle, something like that. This in this side, let's say in the high frequency regime here, we have more or less a straight line. We can have this Cole-Davidson model. Let's say, in my opinion, this Cole plot is very useful because we can actually decide what kind of model we can use, and you can say, okay, is it? You can understand if the depolarization in the time domain will be exactly a pure exponential or not exactly. So usually in most materials we have a stretched exponential that corresponds to Cole or Cole-Davidson, not to the debye model. So let's see some applications. I like this application because it was in my, let's say, my PhD when I was a young guy. Let's say it's one of my first papers in 1991, and that's why I like it very much. This is a study made in lead borate glasses. Okay, this is a lead borate glass with gadolinium oxide. Okay, and here we can see that we have one relaxation here, okay, more or less, and a second relaxation here. It is okay. So now I don't know. Okay, so to make all this let's say very large range of frequency, so I started 1 millihertz, and I went to 10 gigahertz or something like that. So I used several techniques because let's say in that time the impedance meters are not so good as now, and so I used different techniques to measure, let's say, from very low frequencies to very high frequencies. So in the low frequency regime, I used this lock-in technique, okay, measuring the phase between the current and the voltage applied to the sample. So and using this technique, you can also calculate this epsilon prime. So we see here in low frequencies this first relaxation. Here in this medium intermediate frequencies, I use the LCR. In this I regime, I use the reflection coefficient technique. And at very high frequency, let's say microwave frequencies, I use a cavity resonant method. That is a method that, in my case, we can only for each cavity we can use only for one particular frequency. Usually, I use the TA10 mode. Okay, so then I represent here, okay, the cold plot, okay, and I see this in this low frequency regime. I have something like that, okay. In the high regime, I have something like that. Then I try to calculate these relaxation parameters, okay. So only to see what happens exactly. So I use Cole-Davidson, okay, Cole-Davidson, because the circle was more or less deformed. And so I see here in this graphic, for example, these two curves, let's say the red and the black, okay? They have the lead borate. So see, this is a lead borate with two different oxides, gadolinium and neodymium. So I changed the ion, okay? But I maintain the matrix. So, and I have the same beta, this that I called 1 minus alpha, okay? So I saw that they are more or less the same. When I changed the matrix, I made, for example, gadolinium in lead silicate, okay? This 1 minus alpha changes a lot. That is, this low frequency regime reflects the influence of the matrix. Also, to see what happens in the high frequency regime, I do the same. So here I see that the black and the red are the same, okay? That is lead silicate and lead borate with gadolinium. That is, these two curves are for gadolinium. And when I change the ion, the 1 minus alpha changes a lot. Okay, this means that here in the high frequency regime, we are seeing exactly the influence of the ion. So here only to see when the application we made this with PLA, polylactic acid. Okay, we see the peaks here that are moving. Okay, the peaks in epsilon double prime that are moving to the right. This happens. Okay, that is, here we have relaxation that is moving to the right. Then we can make this graphic using the log of the frequency as a function, the inverse of temperature. We can see very well here we have a beta relaxation. So we see here in this graphic we have two relaxations. One here it is, let's say, going to the right when temperature increases. Also here in the low frequency we have another relaxation, okay, that is also moving to the right when the temperature increases. So we can make this graphic. We see here exactly a typical beta relaxation with a straight light with the activation energy, and using VFT we see that alpha relaxation in this let's say in the high at higher temperatures, and we see exactly this nice curve. And usually you use this -2, okay, to calculate the TG, and this is very close very close to the TG that you calculate using the thermal analysis. So finally, another application we can see here, okay, a measure in this particular glass. Okay, we can see several circles. Okay, you can deconvolute this circle, big circle, in several circles. We see a low frequency process, okay, because the frequency increases from the right to the left in this Z representation. So we have here a first relaxation, a second relaxation, and here a very small circle, a third relaxation. So then we try to see using, for example, in this case you use not the debye but this Avriliak-Nagami function with these two exponents. Okay, then we calculate. So we start, for example, with this as we have three circles. We start with these three CPA. This is a constant phase element. That is an element that it's not a resistance, not a capacitance. Okay, it is between them, and actually this can very well fit the data for cold or for Cole-Davidson, for example. And in the case of debye model, this CPA is really a capacitor. Okay, so we made the calculus very simple. We calculate alpha and beta. Okay, and you see that the intermediate frequencies and the high frequency regime process, we have alpha 0 and beta 1. Okay, so alpha 0, beta 1, it is exactly in the debye model. That means, so here you can use this R resistance in parallel with the capacitance. Okay, the second, the same, R parallel with this capacitance. And here the low frequency, no, because we have here alpha, okay, alpha 0.35, 36, and the beta 1, that is, if beta is 1, we are again in the Cole model. That is, we have a debye equal Cole model. So in this case, we must use the you can use the resistance in parallel with the CPA. Okay, CPA is exactly something with like this. Okay, again here we can see if alpha is 0, this is the impedance of a capacitor exactly. So that is, if alpha is 0, we are in the Debye model. So we can represent it by a resistance in parallel exactly with the capacitance. So finally, my team, we have let's say 4 professors. We have some PhD students and postdocs. And finally, thanks for your attention. So if you have questions, I'm ready.
All right. Thank you, Professor Costa, for excellent presentation. And I'm sure students would definitely use all the historical background which you have presented in your presentation. So with that, I open the floor along with my co-chair, Professor Kramer. So if you have questions, either I think there's a chat box which I could see, or raise hand, and then we will entertain those questions. In the chat box, there is perhaps there is a question. I'm not sure. I cannot read. Professor Costa, could you see in the chat box if you can see any question?
Yeah. I would have more a comment. Yeah, as a description by relaxation processes. Yeah, independent if it's a pure Debye relaxation process or Cole-Davidson, Haverlek-Negami. This is just a description, and the question what molecular processes are involved. This is a second, and it's a more deep question. And in order to answer this, well, quite often one has also to employ other experimental techniques, like, for instance, infrared spectroscopy or NMR spectroscopy. I'm not sure if you agree.
Yes, I agree, exactly. I like impedance spectroscopy, but I know that it's not enough to characterize a material. When I decide, for example, for 3 circles, I must have other information from other techniques. So usually, in our case, you use XRD and Raman spectroscopy, FTIR, and things like that. Okay, yeah. TEM. Only because if you have not this information, it's more or less impossible to decide what will be the model. Because sometimes we see something like that. We see, is this one circle, a circle, or can we deconvolute it in 2 circles? So we must have some information about molecular behavior of the materials to decide exactly how to make this deconvolution and how to decide how to do this model. So I definitely agree with you.
Okay, I do not see any hands from students. Is there a question? No? Just not a question, but I saw your presentation with Mendirata. Was that at IIT Delhi?
Mendirata was my PhD supervisor.
Was he from IIT Delhi?
He was from Jaipur, in India.
Okay.
Yeah.
Okay.
But he made his PhD in the United States.
Okay.
So then he met a Portuguese girl. Then he came to Aveiro, and he was my supervisor.
Okay, maybe then different Mandirata because at
Yes.
IIT Delhi, I knew, right.
Yeah.
Okay, so yeah, that caught my attention. But I liked your presentation, as mentioned. You sort of gave a very large overview, which I'm sure students would be able to use for their thesis work. And I'll still continue to see. Well, if Professor Kramer, if there's no question, maybe we could thank Professor Costa
Thank you very
for
much.
his
Indeed.
excellent presentation, and hope to meet in person sometime in the near future.
Yes, I hope so.
Okay, absolutely.
I know that probably
Yeah.
the next Congress will be organized by you, I think.
Yes, as a matter of fact, I just came from after having a site visit in Las Vegas. I talked to several folks and see if we can make that happen. It's a fascinating place. Yeah, I just came about actually 3 hours ago. This is 6 in the morning, so I returned home at 3 in the morning from Las Vegas.
Okay.
So, okay. Well, thank you very much, and I
you.
hope that we meet in Las Vegas next year.
I hope so. Thank you very
Yes,
much.
Absolutely. Thank you so much. Okay.
Yeah.
Now we go back into individual rooms.
Yeah.
I'll be in room A, and Professor Kramer would be in room B.